Fine. So screen is visible, right?
Visible, sir.
Visible, okay. Okay, just a minute. Yeah, actually I have to change the room. Okay, fine. So suppose you have this allylic alcohol, okay, and here I am giving minus DET. So can you tell me what will be the product?
About the plane.
So you have to see in which side allylic alcohol is present. So allylic alcohol is present here on left hand side. So we know for plus DET, what we know for plus DET, we know red wall lal diwar, right? So left means diwar, so that means left means you have to form dash, okay, dash. But this is for plus det. If you are talking about minus det, so you have to just make it reverse. So you will get this, okay, you will get this. Clear? Clear? Okay, suppose you have this molecule, then how you have to do this kind of thing? So first of all, you have to rotate the molecule in the above direction, okay. Clockwise direction you can do, but clockwise will be wrong, okay. This OH group should be always present on the top side, not on the below side, okay, not on the below side, it should be always present in the top side. So if I do here clockwise rotation, the OH is coming in the downside, so this is not possible. I have to rotate in anti-clockwise direction so that the OH can go to the above direction. So you can draw, suppose like this, you have hydrogen right hand side, left hand side you have OH. So when you are rotating by this anti-clockwise direction, you will get this hydrogen this side, and this side you will get this OH, okay. Now here I have two options. What are them? So one is your plus DET, and another one will be your minus DET. Okay, so plus DET and minus DET. Now tell me, if you have plus DET, the epoxidation will happen from which phase?
Wedge.
Wedge. So left side, so lal divar, so it will be formed from your dash bond. Okay, you have to form dash bond. Okay, if you have minus DET, that time it will be what? It will be opposite. If you have minus DET, that time it will be what? It will be opposite. Clear? Nayana, Kaveri, clear? Clear, right? Fine. Now suppose next you have this C7H18, okay. Here you have double bond, here you have OH, okay. So if I use here this, okay, now what you have, 5 mole percentage of what, titanium orthoisopropoxide, okay. Then suppose you have 6 mole percentage of plus DET, you have DCM minus 10 degree centigrade. Tell me the product. Tell me the product quickly.
Below the plane.
Yeah, below the plane. So first of all, you have to rotate it in this direction. Okay, if you rotate it in the anti-clockwise direction, so what you will get? So see, if you are not understanding, see, put hydrogen here, then everything will be clear. If you put hydrogen, so you are rotating it in the anti-clockwise direction. So now hydrogen will be left hand side, this H2OH will be in the right hand side, sorry, left hand side, this hydrogen will be also left hand side, and this side you have C7H18, right? So what you have left hand side, check what they have provided, plus DET. So plus DET means what? Red wall lal diwar, right? So it will be below the plane. So below the plane means what? You have OH here, here you have C7H18, okay, and below the plane, so keep it in below the plane. Clear? Clear, all of you clear? Tell me any doubt.
Yes.
Okay. If I give here minus DET, what I will get? Epoxidation will happen where?
Above the plane.
Above the plane. Okay, so minus DET, write down all the reagent. Because basically the oxygen is coming from this reagent, tertiary butoxide, okay? And you have also the catalyst, titanium isopropoxide. Okay, fine. Now the question is, in which double bond the epoxidation will take place? This double bond or this double bond?
Allylic.
Allylic, because we already told you. Okay, so first of all, if you are not getting, rotate it. Okay, if you rotate it, what you will get? Double bond, hydrogen is in the right hand side, CH2OH is in the left hand side. So again, if you have left hand side, so it should be what? Kabari, tell me, for plus DET left hand side, that means what? It will be lal divar, right? So left means
Slash R.
dash, right? But you have here minus DET. So minus means what? It will be opposite.
It will
It will be opposite. Okay. It will be opposite. So that time you have to form this. Okay. Clear?
If I draw the epoxide below, like
That is also fine. That is also fine. Okay. You can maintain the stereochemistry. That is also fine. If you draw it like this,
it's the same thing, no?
same thing.
Okay.
Basically you have to write down like this, because we cannot write down like this. You have to follow the tetrahedral geometry, right? So hydrogen will be here below the plane. So 1 2 3 4, it is actually a tetrahedral geometry. Okay, done, fine. Now next, suppose you have this isopropyl, you have here, you have double bond, here you have OH. Do it. Below the plane, right? So here you have to write it, rotate it, okay, because this allylic alcohol cannot be present here, okay. You have to bring it to the upper side. If you rotate totally 180 degree, so that time you will get this. So allylic alcohol, and here you have isopropoxide. So left hand side you have plus DET, so it will be what? Dash bond. Okay, don't consider here right hand side, otherwise it will be wrong. This OH should be present on the upper side, not in the down side. Okay. This one. Okay. Clear. Fine. Now next we'll do a name reaction which is very popular. I think all of you also know Wittig reaction. Okay, Wittig reaction. So here, first of all, you have this triphenyl phosphine, phosphorus has a lone pair, and we are reacting this with methyl iodide. Okay, so this is an alkyl halide, and this is what? This is your triphenyl phosphine. So what will happen? Phosphorus will attack from the back side of the carbon. Okay, phosphorus will attack from the back side of carbon. This iodine will leave from here. Okay, so what we will get? We will get this PH3P CH3. Okay, so phosphorus is donating electrons, so it will be what? It will be your positively charged. Okay, phosphorus is donating electrons, so it will be what? Positively charged. Now if I treat this molecule with a base, so what? If you have positive charge, so that means what? It becomes electron withdrawing group. When it becomes electron withdrawing groups, these protons, they are basically becoming what? Acidic proton. Okay, they are becoming acidic proton. So what will happen? So suppose you have CH2 hydrogen. So basically this base will abstract a proton from this molecule, and once it is abstracting one proton, so what you are getting? PH3P plus, and here you will get CH2 minus. Okay, so PH3P plus, and here you are getting CH2 minus. This is known as what? This is known as your phosphorus ylide. Okay, so this is a nucleophile, this triphenyl phosphine, it's a nucleophile. It is attacking from the back side. This is a simple SN2 reaction. Okay, it is attacking from the back side of the carbon atom. Okay, iodine is a good leaving group, so it leaves from here. What we are getting? We are getting PH3P bond CH3. So phosphorus is getting what? Positive charge. If you have base, so base will abstract the proton from this carbon atom, and this what? It is now getting negative charge, and that is what? That is becoming phosphorus ylide. Now this phosphorus ylide is basically two types. Okay, you will get two types of phosphorus ylide. Okay, so one will be your stabilized, and another one will be your non-stabilized or unstabilized, you can say. Okay, so stabilized and non-stabilized. Okay, now if you get stabilized phosphorus halide, so tell me, between E alkene and Z alkene, which one is more stable?
Trans E.
Trans one. So E alkene or trans alkene is more stable. So if you are getting stabilized phosphorus halide, that will form the more stable alkene, E alkene, or I can say trans alkene. But if you have unstabilized or non-stabilized phosphorus halide, that time it will form Z alkene, which is also known as your cis alkene. Okay, so if your phosphorus halide is stable, you will get stable alkene, trans alkene. If your phosphorus halide is non-stable or unstable, that time you will get Z alkene or cis alkene. Now the question is, how do you know that the halide is stabilized or not stabilized? Okay, that is the question. So that we will see. Okay, that we will see. Okay, we will see 1 to 2 examples, then it will be clear. So basically, always keep in mind, when you are checking phosphorus halide stability, you have to check, you have to think like that is, it's a carbon ion. Okay, it's a carbon ion. So if some electron withdrawing group is attaching with this carbon negative, with this carbon, and phosphorus halide means what? Phosphorus halide means this PPH3 plus, you have some carbon minus, so some electron withdrawing group is attaching with this carbon ion, then it will be what? Stabilized or unstabilized? Carbon ion, think about carbon ion stability order. Stabilized. If you have some electron withdrawing group, so that means electrons are flowing towards the electron withdrawing group, this carbon center will become now neutralized because positive charge is generating here. But if you have some electron donating group, okay, electron donating group, that time it will be unstable. So that thing you have to keep in mind. If you are checking the stability of your phosphorus halide, you have to think like this is a carbon ion. So if electron withdrawing group is attaching, that is becoming stable. If electron donating group is attaching, so that time it will be unstable. Is it clear to all? Is it clear to all? Kaveri clear? Nayana clear? Nayana clear? Any doubt?
Yes, sir.
Clear, right? So now I am coming back. So what is the halide we have generated here? PH3P plus CH2 minus. Now the second step of this reaction is, you will have a carbonyl compound. So basically carbon oxygen double bond. Okay, and here I am writing this halide. So CH2 minus PPH3 plus. Okay, so what will happen? CH2 minus, it will act as a nucleophile, it will attack on the carbonyl carbon, this bond will break. Okay, once you do this, so what I can write down? So suppose I can write down here CH2, here you have PPH3 positive charge, and this is becoming what? O minus. So you can see you have minus, you have plus, so what? A bond can form here. Or also I can say, I told you guys that phosphorus oxygen bond, silicon oxygen bond, this bond are very stable bond. Okay, this phosphorus has a high efficiency to attach with oxygen, so this negative charge will donate the electrons on this vacant orbital of phosphorus. You can think like that, or you can just think that oxygen phosphorus bond is very stable. This is a thermodynamically stable process, that much stable it is. Okay, so what we are getting? Oxygen, and here you have PPH3, this thing. So what we are getting? We are getting four membered transition state. Okay, in interview they can ask you, then in UT reaction, what is the transition? Can you draw the transition state? So you have to show this. Okay, four membered transition state you will get. Now what I told you, if you are getting phosphorus oxygen bond, that is actually much more stable than your carbon oxygen bond. So this bond will break because phosphorus oxygen bond is forming, and this carbon phosphorus bond will also break like this. Okay, so what is the driving force here? What is the driving force in this reaction? Phosphorus oxygen bond formation. So in Utig reaction, what is the driving force? Phosphorus oxygen bond formation. And when you are getting this oxygen phosphorus bond, this carbon oxygen bond will also break, carbon phosphorus bond also will break. So ultimately what we are getting this. So see, this bond comes to here, so you will get double bond CH2. This bond moves to there, so this is your byproduct, phosphorus double bond O pH3. So what you are getting? You are getting alkene compounds. Is it clear now? Is it clear now? What is Utig reaction? The mechanism thing is clear.
So,
Tell me any doubt. Any doubt from the mechanism part or Utig reaction? Tell me. Kaveri, Nayana,
yes.
Isa clear? Okay, so
Okay.
okay, fine. So now I am giving a question. You guys try to solve. So see, they will in exam basically they will not give you a normal phosphorus halide. You have to generate the phosphorus halide by yourself. Okay. So this is an exam question. Okay, this is a NET exam question. You just try to solve. Definitely I will solve it out, but yeah, first of all try by yourself. Do it. Tell me what will form. Tell me what will happen. What will happen? So first of all you have this molecule na. So draw it. So this sodium hydride is what? This is what? This is a base, right? So you have sodium plus H minus. This is a base. Now see, here you have two protons. These protons are what? Acidic in nature. Because you have electron withdrawing group in the two sides. Here you have carbon oxygen double bond, here you have phosphorus oxygen double bond. So these protons are very much acidic. So what will happen? H minus, right? What is the base here? H minus. So H minus will abstract a proton from here. Hydrogen gas is releasing. Check, hydrogen gas is releasing, and what you are getting? What you are getting? you are getting negative charge here. Okay, right or not? This step understood. Simple reaction, base is abstracting the acidic proton from here. After that you are getting this carbanion type of thing, right?
Sir.
Clear, right? Now you just check what is the molecule they have given you. This cyclohexanone derivative, right? So I am writing here the cyclohexanone derivative. So double bond O, here you have two methyl groups. So now this negative charge is attacking on the carbonyl carbon. This bond will break. Negative charge will attack on the carbonyl carbon. This bond will break. So what I am getting? Tell me, what should I get? So first of all it becomes O minus. Now with this carbon center, which center is attaching? This center. So this center is attaching. You have what? Phosphorus, double bond O, OET, OET. On the other hand you have this CO2ET group. This thing you are getting?
No, for member ring. Yeah.
Now O minus will attack on the phosphorus because oxygen phosphorus bond is strong. So this bond will break. Again this will come back. One of the OET will leave from here. Okay, one of the OET will leave from here. So what I am getting? So see, here I have oxygen, phosphorus. Okay, here you have CO2ET. Okay, this side you have double bond O, OET. Fine. Now what will happen? What is the next step? After 4-membered ring formation, what is the next step? This bond will
Yeah,
break. This bond will break. Now the question is, which alkene will form here? Stabilized alkene, Z alkene, or E alkene? That is the question. Sorry, E alkene or Z alkene? Yeah.
E alkene.
E alkene. Why? So see, this
Because
ylide is basically, this ylide is what? This is stable because it is in conjugation with an electron withdrawing group. Here you have C double bond O, which is an electron withdrawing group, and here you have also phosphorus oxygen double bond O, so that is also an electron withdrawing group. So I already mentioned you, if you have negative charge and this is attaching with your electron withdrawing group, so that becomes stable phosphorus ylide, and if you have stabilized phosphorus ylide, it will form your E alkene. Okay, so this ylide is basically stabilized ylide, so that's why it will form your E alkene. So how to draw, that is the question. So suppose this is a 6-membered ring. Here you have, now you just form double bond here. Now see how to draw. So CO2ET you have to draw this side and hydrogen this side. Now how to check? So basically this side you have, okay, first of all see, I am talking about this carbon center. So this side you have 2 methyl group and this side you have what? Only carbon is there, right? So that means 2 hydrogen is there. So that one will get first priority and this one will get second priority. Now if I compare the atomic mass of hydrogen and carbon, definitely carbon will have higher, so that will be 1 and that will be 2, so they are trans to each other. Okay, if you write down like this, double bond and this side CO2ET, this side CO2ET, this side hydrogen, so what, this is your number 1 priority group for this carbon atom. First of all check for this carbon atom. So this side your number 1 priority group because you have 2 methyl, this side this is number 2, and this side you have ester group, so this is also number 1, this is also number 2. So here 1 1 they are in the same side, so they will be what, cis. Here 1 1 they are in the 180-degree opposite side, so that becomes what, that becomes trans. Clear? Tell me, Kaveri, Nayana, Is clear?
Finish.
Clear.
Clear, right? I'm going slowly, okay? I'm not getting any speed here, because this concept should be clear, that you will carry out through your, when we will do question answer practice, that time also we will have to do these things, okay? So that's why I am going slow. Now suppose this molecule you are getting this reaction from Wittig reaction, fine. Now I am giving lithium aluminum hydride. What will be the product? If I give here lithium aluminum hydride, what will be the product?
Alcohol.
Alcohol. The ester will reduce into what? Alcohol. Ester will reduce into alcohol. So CH2OH. From CO2ET you are getting CH2OH. Okay. And now this I am giving minus DET. Okay. Tertiary butoxide and titanium isopropoxide. Tell me.
Above the plane.
Above the plane, right? Yeah. So left hand side you have, so it should be dash, but you have minus DET, so you have to change it. You have to change it. So what I will get? This one. Okay, so this was the question from your NET exam basically. Okay, so yeah, that's it. Okay, so initial reaction was Wittig reaction. After Wittig reaction they are doing reduction with lithium aluminum hydride, and then they are doing Sharpless asymmetric epoxidation. Okay, Sharpless asymmetric epoxidation. Fine, clear.
Yes, sir.
Clear, right? Okay, now you have this. So here you may be wondered that lithium aluminum hydride can do what, because we do not have any functional group. So just write down one line that triple bond adjacent to allylic alcohol, triple bond adjacent to allylic alcohol is reduced to transalkene, so that means E alkene. Okay, so that is the information I want to give. Apart from that, I think you can do now. Okay, so if you have an allylic alcohol in the adjacent position, you have a triple bond, you will get transalkene or E alkene. Okay, if you have this compound also triple bond and then you have CH2 and H2, if you have amine functional group, that time also it will act as same, you will get transalkene. So alcohol and amine both will give positive with this lithium aluminum hydride, you will get E alkene. Okay, draw it and then tell me the final product.
beta gamma epoxy group.
Which plane, above the plane or below the plane?
Uh, Below the plane.
Below the plane, how you are getting? Okay, let me check. So first of all, E alkene will form, right? So see, if I see here, so this is your bond. Okay, so it's better to give numbering, so you just give 1 2 3 4 5 6 7 8, right? So here also I am giving 1 2 3 4 5 6. Now trans alkene you need, right? So trans means it will be like this, 6 7, and here you have CH2, which this is your number 8. Now why it is trans? You can see hydrogen is in this side and this hydrogen is in this side, so they are trans to each other. Okay, so this is the actually product you will get. And cis alkene means how you have to draw cis alkene. So that time you will get C double bond and then make CH2 which this side. So what, both the hydrogen you are getting on the same side. You can see this is, if I consider this carbon atom, so this is your number 1 priority, this is your number 2 priority. This carbon atom number 1 number 2, so they are in the same side. Here double number 1 priority is there, number 2 priority is there. Here you have carbon, so this is your number 1, this is your 2. So 1 2 1 2, so that means it is your trans alkene. Fine, so this is the E alkene you are getting here. Now after getting this E alkene, what they have given? They have given you plus DET. Okay, so now tell me, this CH2OH group is present on the right hand side or left hand side? I have to rotate it first of all. Okay, I am just rotating only this part. So if I rotate it in anti-clockwise, this double bond will rotate like this, na? So it is coming like this vertical. So now tell me, CH2OH is present on which side? Right hand side, na? If I rotate it anti-clockwise, this CH2OH group is present in right hand side. If you have right hand side and you have plus DET, what you will get? Red wall, lal diwar. So that means what?
Above the plane.
Dash bond above the plane. Okay,
Above.
so you will get okay, and here you will get this above the plane. Clear? Kaveri, Nayana, clear? Tell me any doubt.
Perfect.
Clear, right? Okay, fine. So if it's clear, now these questions you guys do. So if you use plus DET, you will get one compound. If you use minus DET, you will get another product. The rate constant for the first is K1 and rate constant for this minus DET is K2. Now you have to tell me where the rate will be much faster. K1 is greater than K2 or K2 is greater than K1? That is the question. Do it. So if I use plus DET, the epoxidation will happen from which phase?
Below.
Below the plane, correct. So first of all, you have to rotate the molecule 180 degrees so that this allylic alcohol can come to the upper side. Okay, if you rotate it, that time which side you are getting this? Left hand side. Okay, left hand side you will get. So basically lal diwar. Okay, lal diwar, so that means what? You will get in dash bond. Okay, so oxygen is there. This, if you have minus DET, so already you know that will be opposite, right? So opposite means you just make it above the plane now, above the plane. Okay, now the question is which rate will be faster, this K1 or K2? What do you think? So here if you see, above the plane you have a methyl group which is a bulky group. Below the plane you have hydrogen which is a small group, right? Here the epoxidation is happening from below the plane. So above the plane you have bulky group, below the plane epoxidation is taking place. Here above the plane you have methyl group, bulky group, and above the plane itself the epoxidation is taking place. So that will be actually slower. Okay, so K1 is greater than K2. Is it clear? It is less hindrance, huh? This plus D, it is becoming what? Less hindrance. Okay, why? Because the methyl and the epoxide ring, they are opposite to each other, but here methyl and epoxide ring, they are present in the same page, same plane. Okay, so they will do steric hindrance. Is it clear? Clear, right? Okay, now what about this? So now just tell me quickly, K1, K2, which one will be higher? First of all, write down the product, try to find out the product, then tell me K1 is greater than K2 or K2 is greater than K1. Quickly.
K2 greater than K1.
So if I give you a plus DET, epoxidation will happen from which phase? Yeah, which plane?
Below the plane, sir.
Below the plane, correct. So below the plane epoxidation is happening. Okay, and if I use minus DET, that time it will be opposite. Okay, double dash, that time it will be opposite to your plus DET. So below the plane I have methyl group, above the plane I have proton, and here the epoxidation is happening from above the plane. So you can see here this methyl, which is actually a bulky group. This bulky group and epoxide, they are forming on the same side, so that will be a slow reaction. Here the bulky and epoxide, they are in the opposite plane, so that will be a what? Fast reaction. So what? K2 is greater than K1. Okay. Kaveri, clear?
Yes, sir.
Okay, fine. So that's it for surface asymmetric epoxidation. Okay, now next we have next topic, that is dihydroxylation. Dihydroxylation. Okay, so first of all, write down what do you mean by dihydroxylation. That addition of 2OH. Okay, addition of 2OH on double bond. Okay, addition of 2OH on double bond. So that is basically what dihydroxylation. Number one reagent comes what? Osmium tetroxide. Okay, osmium tetroxide. So the structure of osmium tetroxide is like that. Okay, structure of osmium tetroxide is like that. Okay, what will be the oxidation state of osmium? What is the oxidation state of osmium here?
8.
+8. Right, here also you are getting +8. Okay, so +8 means what? +8 means this osmium is becoming highly electron deficient. Okay, highly electron deficient. +8 means what? It's an electron deficient molecule. Okay, now next write down that electronic effect of oxygen is vanished due to +8 oxidation state of osmium. So what does it mean? So as osmium center is very highly electron deficient, the oxygen is actually donating the electrons to the osmium center, or I can say the electrons are actually tries to flow to this highly electron deficient center. Okay, so that means oxygen lone pairs are not available. These oxygen's lone pair are not available for what? Hydrogen bonding. Okay, so if you are using only osmium tetroxide, that time hydrogen bonding is not possible. Why? Because the oxygen lone pairs are already busy to osmium center, okay, to make it electronically rich. Okay, so no hydrogen bonding you will see in case of osmium tetroxide. If it is only osmium tetroxide, then okay, and definitely it will do syn dihydroxylation. So syn means what? Syn means same side, cis. Okay, syn dihydroxylation, or you can say it cis dihydroxylation. So these are the things. Clear? These are the points you have for osmium tetroxide. So osmium center is highly electron deficient. Electronic effect of oxygen is vanished due to +8 oxidation state of osmium. Okay, no hydrogen bonding is there, and this is doing what? Syn dihydroxylation. Okay, now suppose you have this double bond Okay, this double bond you have, so osmium tetroxide you have, right? So osmium double bond O, double bond O, double bond O, double bond O. So what will happen? See, this oxygen will attack on this double bond, or you can think like that this double bond is attacking on the oxygen. Why? Because this oxygen is already busy. This oxygen is already donating the electrons to the osmium center, so this oxygen is actually becoming now electron deficient, so double bond can also attack here. Okay, so what will happen when it attacks on the oxygen? This bond will break. Okay, this bond will break automatically. This bond will break and it will attack on the other carbon center. So what you are getting? You are getting like this. So oxygen, here also you have oxygen, here you have osmium, osmium, double bond O, double bond O. Now see, what is the oxidation state now? So now the oxidation state is becoming +6, 2 from here, 2 from here, +1, sorry, -1, minus. So basically you will get +6 oxidation state here. Next step you have water. Okay, so now water will attack from this side. This is actually like your square planar compound, so you have two vacant orbital. From above the plane or below the plane, water can attack. Okay, so basically water will attack, okay, from below the plane also as well as from the above the plane also. From both the side water will attack on the osmium center, and when it attacks, what you will get? So here you will get water, OH2. Here also you will get what? OH2. Okay, OH2 means what? It will be positively charged, it will be also positively charged, because water is donating electrons, so it will be positively charged. Okay, next step will be what? Next step, this oxygen will take up the proton from this water. Okay, this oxygen will take up the proton, one of the oxygen from here. So ultimately you are getting this kind of thing. Now this oxygen is forming 3 bonds, so it will be positively charged. Positively charged. Here you have osmium. Okay, here you have OH, OH, double bond O, double bond O. So if you are getting a positive charge, so this bond will break. Again, this bond will break, because positive charge means what? It becomes now good living group. Positive charge means electron withdrawing, it becomes now good living group. So ultimately what you are getting? See what you are getting? Diol compound. Okay, syn diol you are getting. Is it clear? What is the byproduct you are getting? Byproduct you are getting this. Is it clear? Mechanism is clear? Tell me any doubt. Osmium tetroxide mechanism is clear.
Because of the lack of H bonding and lone pair, the double bond has to be electron rich, no?
And double bond has to be electron rich. Electron rich. Here I have given you substituent, right? This.
Okay.
Osmium is electron deficient, so that means definitely the double bond should be electron rich. Okay, if one center is electron deficient, other center should be electron rich. Okay, clear? Clear. Mechanism you have any doubt? Tell me. Right. Fine. Now write down some points. So suppose you have osmium tetroxide. So basically this is your costly, okay, costly and poisonous. Okay, costly and poisonous. And if you have NMO, okay, so NMO, you know what is NMO? Write down N methyl morpholine, N-methyl morpholine, N-oxide, N-methyl morpholine, N-oxide. So this is the structure of your NMO. Okay. So this is the structure of your NMO, N-methyl morpholine, N-oxide. So this osmium tetroxide is basically very poisonous. Okay, this is costly and poisonous. Okay, so that's why we are using some NMO. So NMO, what is the role of NMO? Okay, one question they generally ask, that you are using osmium tetroxide, that is fine, but why you are using NMO? So what is the role of NMO here? So NMO is acting as a co-catalyst. Co-catalyst. Now what is the role of co-catalyst? So co-catalyst means this is not your main catalyst. Main catalyst is your this osmium tetroxide. So what is the role of co-catalyst? So it will regenerate your catalyst back. So this is, I already mentioned you, costly and poisonous. So that actually we will use in very low amount. Suppose you will use this around 10 mg. This one you will use in 10 mg, but this NMO you will use in like you can use in 300 mg or like that. Okay, NMO you can use, but this main catalyst, which is costly as well as poisonous, that we will use in low amount. Now why in low amount? So basically if we are using NMO will try to regenerate the osmium back. Okay, NMO will try to regenerate the catalyst back. So if I show you, so here osmium tetroxide is +8, here osmium is becoming +6. So that means what? The reactivity depends. Now with the presence of NMO, this reagent again it will come back to this state, osmium tetroxide +8 state. Okay, so this is the role of NMO. They can ask you what is the role of NMO. Okay, clear? So NMO means what? NMO will regenerate osmium tetroxide, and we will use it in very low amount because it is costly and poisonous, and NMO's main role is that. Fine. Okay, now we will do some example. So suppose you have this molecule. You have this. Okay, now if I am using here this osmium tetroxide in presence of NMO. Okay, osmium tetroxide in presence of NMO. Water is the solvent, or you can use acetone as well. Okay, water acetone mixture you can use. So tell me, the dihydroxylation will happen in which?
Left one.
Left one. Why not the right one?
Because of electron withdrawing group present, so to make it equal.
Yes, electron withdrawing group is present. So this double bond is basically your electron deficient, and this double bond is actually comparatively electron rich. Now the question is, dihydroxylation will happen, that is fine. Which phase, which plane?
Sin, both will be above the plane.
Above the plane. Why not below the plane?
Because this is
dihydroxylation.
exo-endo.
So this system we have done, no? This kind of system you have.
Yep.
This system is similar to this. See. So you have nothing is attached here on this carbon. So what you have? You have hydrogen, right? So if you have hydrogen, so that means the osmium will approach from this side only. Okay, the osmium will can approach from above the plane. If you have methyl here, that time the osmium has to approach from the opposite face. Okay, if you have hydrogen, so that time the osmium will approach from above the plane, But if you have, instead of hydrogen, if you have methyl here, that time definitely the osmium will have to approach from below the plane.
Sir, I have a question.
Huh.
This will make sense if there is no NMO, but if NMO is there, it is regenerating, right? So
Regenerating.
after NMO is present as co-catalyst. So
Co-catalyst.
osmium tetroxide is regenerating again, no? So then after all the left side double bond are hydroxylated, the right side can also happen.
You will use in 1 mole, na? With respect to that, you will use in 1 mole.
Yeah, but NMO is present, so it doesn't matter, right?
No, it matters, na? Suppose you are taking this compound 1 mole, you are taking this reagent also 1 mole. Okay, NMO maximum you can take 1.2 mole, not more than that.
1 mole of osmium tetroxide will oxidize the double bond. Then that 1 mole is over, but then NMO 1 mole is left. That will convert the reduced osmium oxide, osmium tetroxide to osmium tetroxide, the original form. Then again 8. It will reduce.
Plus 8. Correct. Correct.
Again reduce, no?
No, it's not like this. Suppose here we are just seeing 1 molecule, right? So 1 mole means what? 1 moles means you have Avogadro number of molecules, na? So it will do 1 by 1 like that. That's what I am trying to say. Here we are just seeing only 1 molecule, but in general if you use 1 equivalent or 1 mole, so that time you have that much molecule, na? Avogadro number of molecules you have. So basically when NMO is regenerating, that time osmium can actually oxidize another molecule of the same reactant.
Okay.
Clear? Tell me any doubt. 1 mole means it's not only 1 molecule, right? You have, suppose you have 100 molecules of this same reactant, 100 molecules you have osmium tetroxide. Now actually we cannot use that 100 molecules. That osmium tetroxide we will do like this, 0.5 mole like this, 0.5 equivalent we will use. Okay, we will reduce the amount of that, and we will increase the amount of your co-catalyst. That's it. Okay. When you will do that time you can get. Okay, but yeah, again I am saying that you will use suppose this catalyst are very costly, huh? Even your platinum, palladium catalyst, they are very costly, so that time you have to use one co-catalyst. So basically this kind of catalyst, suppose this palladium catalyst is so expensive, you just use their 0.01 equivalent, that much you are just using, so you have to use one co-catalyst. Okay, that co-catalyst you can use one equivalent. Okay, and you have 1 mole of this, so basically it will regenerate again and again, and that will actually do. Clear? We will reduce the amount of your catalyst, we will increase the amount of co-catalyst. That's it. So the main thing will be same. Clear? Clear? Any doubt?
Yes, sir.
Clear, right? Okay, now do this one. Okay, do this quickly because now you know. Okay, so if I use here this osmium tetroxide in presence of NMO, sin dihydroxylation will happen. Tell me from which phase?
Above.
Why above? Why above the plane? Hydrogen bonding is not possible, na? Here I have written, na, no hydrogen bonding. Okay, no hydrogen bonding. If you have osmium tetroxide and NMO, the oxygens are busy to donate the electrons to the osmium center, so they are not that much electronegative here. Okay, what I showed you here, I have shown na, oxygens are busy to donate the lone pairs to the osmium center. They don't have the available lone pairs to donate to interact with the H plus of OH bond. So this interaction is not possible here because oxygen is already donating the electron density to the osmium center. Okay, so here no hydrogen bonding, and if you have no hydrogen bonding, that time the dihydroxylation will happen from below the plane. Clear? Write down here no hydrogen bonding. Clear? Clear? Now suppose you
Yes,
are
sir.
using osmium tetroxide in presence of NMO and you are using tameda. What is tameda? What is tameda?
Tetramethyl ethylene
Tetramethyl ethylene diamine. So what is the role of tameda?
chelating.
Chelating. So now this nitrogen has lone pair. So if you have osmium tetroxide, okay, which is highly electron deficient, now this nitrogen will donate the lone pairs to the osmium center. Okay, so if you use tameda, that time nitrogen is donating the lone pairs to the oxygen center to make it electronically rich. Okay, so that time your oxygen lone pair is available. Okay, that time oxygen will have electron density and that can form hydrogen bonding with the OH bond. So if you use tameda, that time you will get hydrogen bonding, and that time the dihydroxylation will happen from above the plane. Clear? The difference is clear. What is the difference? So here you have hydrogen bonding. So if you use some chelating reagent like tameda, so they are donating the electron density to the electron deficient osmium center, and when it donates, so that time oxygen gets back its electrons. Okay, oxygen gets back its electron density. So now it can do hydrogen bonding with the any other electropositive element OH. Okay, clear? Clear? Kaveri, Isa, clear?
Clear.
Yes, sir.
Fine, I am going very slowly, okay? So try to understand properly because this topic is important. They usually ask questions from here. Okay, in interview also this is important. Okay, they can ask you. So osmium tetroxide, and here you have NMO. Okay, and here I am using osmium tetroxide, NMO, and tameda. Tell me the product quickly.
Both will be below the plane.
Both will be below the plane, correct. So here no hydrogen bonding because these protons are not acidic. If you have direct oxygen hydrogen bond, that time the proton becomes acidic, but if you have OCH3, that time no hydrogen bonding. Okay, whether you are using NMO or whether you are using tameda, no change will be there. So here this will be below the plane. Okay, if you use tameda also, that time also you will get below the plane, correct. Good. So here no hydrogen bonding in both the cases. Okay, no hydrogen bonding. Here also you are getting no hydrogen bonding. Is it clear? Write it down. Done. Okay. So now suppose you have this molecule. Do it. Tell me the product.
Below the plane.
Below the plane, right? So first of all, draw this molecule in chair form, okay? So CH3 is present above the plane, so keep the CH3 here. Hydrogen is present below the plane, so keep hydrogen here. This is your trans-decaline system. Trans-decaline system. So now tell me, the nucleophile can approach from above the plane? No, right? Because you have already methyl group present there. Already you have a bulky group there. So above the plane approach is not possible. So you have to approach from below the plane. So this osmium tetroxide is also a bulky group. Okay. So it has to approach from below the plane. Okay. It cannot approach from above the plane due to this bulky methyl group. So once it approaches, what you will get? So here you have CH3, here you have hydrogen, you will get an intermediate like this, oxygen, this is connected to your osmium center. Like this you will get an intermediate. When you do hydrolysis of that, water will come and you will get back to your OH. So basically I am drawing the final product here in a cyclic form. So methyl is present above the plane. Okay, hydrogen is present below the plane. OH is attaching in where? Below the plane. Is it clear? Is it clear?
Yes.
Clear, right? Okay. Now suppose you have this. Here also I am using osmium tetroxide, but only one equivalent. So tell me, the dihydroxylation will happen in which double bond? This double bond or this double bond? That is the question.
The left side.
Left side, why?
Because more electron rich.
More electron rich. So that is the reason. So here you are getting this double bond is what? Disubstituted. But if I talk about this double bond, so 1, 2, 3, 4. This is tetra substituted, right? This double bond is tetra substituted. So more substituted double bond you have. So which one is actually your more substituted? So the dihydroxylation will happen there when you are giving some stereochemistry. So if you are giving above the plane for this OH, you have to place above the plane for this OH also. Okay, or you can show below the plane for both the OH. So this is what, this is your scene. Dihydroxylation. Scene dihydroxylation. Is it clear? Tell me, we are done. Kaveri, Nayana, Isa, clear? So today, what we have discussed, few things: surplus asymmetric epoxidation. Okay, surplus
Yes.
asymmetric epoxidation. Then we have done Wittig reaction. In Wittig reactions also we have included a surplus asymmetric epoxidation. After that we are coming to this dihydroxylation part, and here we have just discussed one reagent only, that is your osmium tetroxide. No hydrogen bondings in dihydroxylation. If you are using osmium tetroxide in presence of NMO, what is the role of NMO? NMO is the co-catalyst to regenerate the catalyst. Okay, and if you are doing with only osmium tetroxide NMO, no hydrogen bonding, but if you provide tameda, so tameda will provide electron density to your osmium center and it can now do hydrogen bonding. Okay, so just go through the examples and then tell me if you have any doubt. Is it clear? Okay,
Yes.
next day we will do surplus asymmetric dihydroxylation. Then we have Bayer's reagent, Woodward's reagent. So basically in this dihydroxylation part we will get 3 to 4 reagents, then we are done with that. Okay, we are at the end of our reagent chemistry, but hardly it will take 2 to 3 more classes, then we will be done. Okay,
Yes,
fine.
sir.
Tell me any doubt.
Yes, sir. Clear, sir.
Clear, right? Okay, fine. Okay, okay, then bye.
Thank you, sir.
Okay, thank you. Bye.